Hello YouTube! Today we're going to be talking about torque. Torque is the force equivalent for angular motion. So we're kind of skipping through the units one day at a time and we're being like, it's the first unit but spinning, it's the second unit but spinning, it's the third unit but spinning, and so that just is going to keep happening. So, let's do it. Ideally, end of the day, model the motion of rotating objects using Newton's second law for spinning things. So to start out with that, we've got the right hand rule. And torque is the equivalent of angular force. Basically, we're saying it's the force on it that causes it to accelerate rotationally instead of the force on it that causes it to accelerate linearly. Now, a force that provides a torque, meaning a force that causes something to spin, will also cause it to move if nothing's holding the object in place. So just something to be aware of is that anything that's going to cause angular motion can also cause linear motion, can also cause it to move sideways. Or accelerate sideways, I guess, for being more careful. Just like force, more force means more torque, right? The harder you push it, the more the thing's going to try to spin. The one other thing that matters for that, though, is the moment arm, which is the distance away from the pivot you're pushing on, and that will also matter. Brake for push door, what that means is take a sec, try to push a door open by going as close as you can to the hinge and then putting force on it. And then try to push it just as hard far away from the hinge. What you'll find is that it's a lot easier to open the door when you push your thumb very far away from the hinge as opposed to very close to the hinge. And that's because even though the door hasn't gained any extra moment of inertia, it's the same door around the same pivot with the same mass and the same shape. What's really different in those two scenarios is that because the force is being applied from further away, you're getting a lot more torque. So there's two things that matter for radius. The first of which, and this one goes with r squared, is that the further something is away from the pivot, the harder it is to make it spin. So the more mass you bring away from the pivot, the harder the object is to cause to rotate. The second thing is that the further away from the pivot you push, the easier it is to make that object spin because the more torque you're going to get. One of them is a product of the object. The rotational inertia is basically like the mass of the object. The shape of the object compared to what it's pivoting around is more a property of the object itself. The second one is more of a property of the situation and what's being done to the object. So if you change what you are doing to the object, you're changing the torque on it because you're changing where you're pushing from and what direction you're pushing in. That last one is also relevant for torque. It's not on here, but should be. The third key component for torque is that it's a cross product. And what that means is you're doing vector math where you multiply two vectors, perpendicular vectors, and you get a third perpendicular vector. That's your torque vector. Cross products scale based on the amount you are pushing, based on the angle between the two vectors that you're multiplying. So torque also scales based on how you push it. And we'll deal with that when we actually get the equation up on the screen. The right hand rule for direction, and if you're particularly, you have no way of knowing this. This is my left hand, so if I kind of get some stuff backwards, that's why, but it's to make it so that it looks correct for the right hand rule when my camera is flipped. So if the force is going towards the screen or towards you and to the right, left on the screen, towards you and to the left, then the torque on that from that force will be going up. Vector A is your first vector, in this case, the displacement vector going from where the torque is to the torque itself. Vector B is your force vector, so you point in the direction that the thing is getting pushed next. And when you do, your thumb will tell you which way the torque goes. Something that's a little weird about this is that if an object is spinning like this, and you're putting forces that cause it to try to spin in one of these two directions, These two directions are going to have torques and angular variables that are either going up or down. If it's up, it'll be because it's spinning. Again, this is all kind of mirrored from what it should be. If it's up, it'll be because it's spinning like this from my perspective. Although watching it on the screen, God, this is hard. It's going to the right when it's coming across the front. So, oh no, it just stopped mirroring and we're good. Great. So this is going up for the torque because if I take my right hand, and I use my right hand to model what the torque is doing, and I should actually turn so that it's sort of looking at it the way that you'll see it. The object is spinning this way, and so I take my right hand, I put it the way it's spinning. That thumb shows me the direction the torque goes. Perpendicular plane, a line perpendicular to the plane of the two. So it's either going to be up if it's this way, or if it's spinning this way, curving my hand along with how the thing is spinning, my thumb goes down, that's the direction of the torque, down. Same thing applies to the angular motion variables, actually. Theta, omega, and alpha are all going to go on lines perpendicular to the plane of rotation. Yes, kind of hard to show through a video. Sorry. So the equation for this is that your torque is going to be equal to R cross F. What R cross F means is that you take the R, you multiply by the cross product of the force. The size of that vector, so that's what the two absolute value symbols there mean, is going to be such that if you multiply R, the distance away from the pivot, the moment arm, to the force, F, the size of the force, and sine theta, where theta is the angle between R and F. You have to be really careful about that. It's not just whatever angle they give you for the problem. It's always, always, always the angle from R to F. And the sine of that angle is going to give you, times the other two is going to give you torque. So what's what's good to note about that is that when your object is getting pushed such that the two vectors are at a 90-degree angle, meaning you have a radius line on the thing you're trying to rotate, and you're pushing it perpendicular to that radius line like this. In that case, you'll get the most torque you possibly can because the sine of 90 is going to be 1. If you are pushing straight towards the center of the circle or straight away from the center of the circle, you will get absolutely no torque. That doesn't mean you won't make the thing accelerate, but it does mean that doing so won't make the thing spin. So if you ever grab a wheel and you have it in the air, if you push the wheel towards the center of the wheel won't start spinning. If you push the wheel away from the center of the wheel, it will. Yes. So there's 3 ways that you can get no torque. You can either not push it, meaning no force. You can try pushing it on the pivot point. If you do that, it won't spin because you have no torque, because you're not pushing away from the center. And then the third one will be if you're not pushing in a direction that is away from the center, but not completely away from the center. It has to have some tangential component of the force. The other way you can think of that, the only component of the force that causes the thing to spin is the component of the force that's tangent to the circle that it's trying to spin around. If you push it radially to the circle, you're not causing a tangential acceleration, so you don't get angular acceleration. Great. So, quick example. A person applies a force to of 20 newtons straight down on one end of a 20-meter seesaw. What is the torque exerted on the seesaw? So taking that and copying it down, we've got our little seesaw. We know that it is 20 meters long, and there is a force of 20 newtons going straight down from this location. This is our pivot right in the middle, and we're good. So going through, solving this out. I should actually make sure I'm paying attention to what the questions are actually asking. So for part A, it's what's the torque? For part B, it's force at 7 meters away. I don't know why I didn't make these numbers work out well, but I didn't. And then for C, I'm missing a Y. It should say how much would they need to exert to create the exact same torque if they're applying a force on the other end of the seesaw at an angle of 37 degrees from the vertical, and in what direction. Great. Okay. So for A, nice and straightforward, torque is equal to R cross F, which in this case is going to be our R of 10 meters times our force of 20 newtons times the sine of our angle between those two forces. And because we've got our R of 10 meters and our F of 20 newtons, and the angle between those two is such that it is perpendicular because one is straight down and one is side to side, we know that sine of 90 is going to give us 1, and we don't have to care about it. So we get 200 Newton meters, yes, the units are joules, of torque. So yeah, actually I should mention that. The units for torque are really kind of dumb. They're energy units. It just kind of is what it is. Yeah. So torque is measured in Newton meters. For B, now what we've got is a similar situation, but we're trying to get a torque of 200 Newton meters, but negative. And I should actually be careful about this. If they're pushing the left end of the seesaw, using the right hand rule, the torque is going to the left. The force is trying to get it to spin down. So left of the pivot spinning down means that our torque will come out of the page or towards you. If it was on the other side, it would be to the right of the pivot, and when I curve, it's still spinning down, so it would be going into the page. Versus what we would need to do here to get something going into the page is if it's to the left of the pivot and we want to try to spin it the other way, we're going to have to spin it up, which creates a torque going down into the page. So for B, when we're trying to get the same torque but negative, the way we would do that is by applying a force 7 meters away from the original force, which, because the total is 10 meters, means 3 meters away from the pivot point, so R equals 3, at an angle of 37 degrees from the vertical. So this was kind of me trying to make everything a little bit annoying. Our torque is 200. Our R is 30, but our theta needs to be the theta between our force and our moment arm, which is not 37, it's 53. So when we're solving for our force here, RF sine theta, our equation's going to be straightforward till we throw the numbers at it. We're just going to have to be really careful about which numbers we throw at it. Dividing by r sine theta, dividing by r sine theta. We'll get that our torque divided by r sine theta is going to equal our force. Our torque is 200, our r is 3, and our sine theta, sine 53 degrees. Oh god. Sine of 53 is going to be the tall one, so 4/5 is going to give us 20 over 4, which is 50 times 5, which is 250 over 3. So 250 over 3 Newton meters. Just Newton, sorry, it's a force. So this is a lot smaller. That shouldn't be right. 2,500 over 3. There we go, there we go. No. 50 times 5. Our force is to generate the same force, closer in, torque, closer in, we'll need more force. Oh, yeah, which we definitely have. Sorry, I flipped what the force and the torque were. We have 20 newtons of force originally. To get that same amount, we're going to have to use somewhere around 70 newtons of torque, 80 newtons of torque, force, 80 newtons of force to generate the same torque of 200 newtons, because we're much closer in, and now we're at an angle instead of pushing straight at a 90 degree. If either of those had been happening alone, it wouldn't have been as big of or as exaggerated of an effect, but because they're both happening, it's a much more exaggerated effect. All right, for C, we're being asked if we had it at the... Oh, shoot, I think I combined the two. That I did. I combined the two. So for this one, we should have had a theta of 90 still. So it should have been 200 over 3. For this one, we should have a situation where our radius is still the 10, but our angle is off. And we're going to have to push up to create the same torque. Sorry, we're going to have to push down on the right to create the... If it's the exact same torque, it'll be up. If it's the same torque but negative, it would have to be down. Because what's happening is that when our R cross F is on the left of the pivot, pushing down creates a torque going upward. But when it's on the right of the pivot, if we want to make our thumb go up, the way we do that is we curl our hand so that on the right it's going up, and that'll do the same thing. So we have to push up on the right to create the same torque as down on the left, or down on the right to create the opposite torque as down on the left. And math-wise, it'll be the same as the thing that we just did, except with a 10 and the sine 37 instead of the fixed sine 90. Okay, so Newton's second law for torque, and I'll swap over in a sec. The equation is kind of what you would expect if you're just comparing the two equations, and you were like, all right, we'll make it everything angular. We're taking our old equation, which is that net force is mass times acceleration, and we're saying, okay, well, r cross f is torque. So I need to multiply each side by the radius. And if I want to get from linear acceleration to angular acceleration, it'll be mass alpha times r. Well, this will give me mr squared. And I'm probably doing that for the summation of all forces along the entire object. So it's probably the I for the entire object. And when we've done that, what we'll get is that torque is equal to I times alpha. So we're taking our old equivalent of force and we're popping it into angular. We're taking our old equivalent of mass and we're popping it into angular. We're taking our old equivalent of acceleration and we're popping it into angular. Things to be mindful of for all this. The angular acceleration of the entire object will be the same. But the linear acceleration of the further out pieces will be greater than the linear acceleration of the closer in pieces. Additionally, don't forget that your torque is going to be r cross f. And don't forget that your moment of inertia is going to depend on the shape of the object, not just the mass of the object. So if something is harder to accelerate angularly because of its shape, it'll accelerate less. So, popping that over for an easier example and then doing a harder example. We've got a 2 kilogram 0.35 meter radius bike wheel. I'm going to do capital R for the radius of the whole thing. And it's rotating 20 times in 10 seconds. When we apply a brake force, going backwards at 100 newtons with a coefficient of so the normal force between the brake and the tire is 100 newtons. Our coefficient of friction is 0.8. How many times will the bike wheel rotate before stopping? Oh, wow, I did not make this one straightforward. The individual components of what's going to be happening are very easy. Actually doing it out is going to be very annoying. Honestly, it would probably be faster with energy, but we're going to do it with the stuff that we've learned so far. Let's hop to it. I'm asked how many times the bike will rotate before it stops. Well, if I take theta, the angle that it rotates, and divide it by 2 pi, the number of degrees in a single rotation, that'll give me the number of rotations that it does. In order to get theta, I'm probably going to have to use something with kinematics, right? Because I've got like current number of rotations and the time it takes to do those rotations. So I could find the initial angular velocity, which is going to be that it completes 2 pi times the number of rotations degrees per time, 10 seconds. So this is taking our theta and dividing it by our time. And that'll give us our initial angular velocity. We've got an initial angular velocity. We've got a final angular velocity of 0 because it's stopping. And we have a force. We've got a radius. We can turn that into an acceleration. And between those, we'll have 3 of the 5 that we need. If we get our acceleration, we'll have initial velocity, we'll have final velocity, and we can find angular displacement. Once we've found our angular displacement, we can figure out what our number of rotations was pretty quickly. So This is our initial angular velocity coming from 2 pi radians in every single rotation times the 20 rotations that we do to give us the number of radians we go through, divided by 10 for the amount of time that it takes. Our final angular velocity is 0 because we're not spinning after we stop. To get our torque, that'll need to equal our moment of inertia times our theta. Oops, sorry, times our alpha. This will get our alpha. The problem is that in the past when we were doing equations like this, we could just do force equals mass times acceleration. For this one, it's trickier because if we want to find our torque, we're not just going to add up all our torques most likely because we're not going to know all our torques. In this one, we don't know the torque, we know the force. So what we can do is R cross F as our torque, set that equal to our moment of inertia times our acceleration. Well, our R is 0.35, but our force is going to be the force of friction, which we still need to figure out. I'm just going to label this as R cross force of friction. Now that'll be equal to our moment of inertia for our wheel. If we're assuming that our wheel is pretty much a hoop, we're going to have the mass of the wheel times the radius of the wheel squared times our alpha. And I should write that. Our mass for our wheel was 2 kilograms. So from there, if we're looking for alpha, we are going to need to find our force of friction first. So force of friction is equal to normal force times our coefficient of friction, which is going to be 100 times 0.8, which is 80. So we've got 80 newtons of friction. Now that we know our force of friction, we can find our angular acceleration and sort of follow our roadmap to finding our actual answer. We're dividing each side by mr squared. One of the radiuses is going to drop from the bottom, and the radius from the top is going to drop. That's going to give us that our angular acceleration will be equal to our force divided by our mass times our radius. Great. If we take that, we now have an equation that we can use where we want final velocity, initial velocity, flipping on those from what I pointed on, our acceleration, and our displacement. So we don't want time. That'll give us final velocity squared equals our initial velocity plus squared plus 2 times our angular displacement times our angular acceleration. Solving for angular acceleration, this one's going to be 0. So if we do minus omega naught squared, I'm going to need to be a little bit careful. Our angular acceleration is going to be negative because our torque's got to be negative to get this thing to actually stop. So I should have thrown a negative sign on both of those and on here as well. So we'll get omega squared negative omega naught squared equals 2 times our angular displacement times our acceleration. Divide each side by double our acceleration, divide each side by double our acceleration. And we'll wind up with negative omega naught squared divided by 2 times our acceleration, which is equal to our change in angle, but also equal to negative 2 pi times 20 divided by 10 squared, divided by 2 times our theta, which is our force of friction, which was 80. Our mass is going to be on the top 2. Our radius is going to be on the top 0.35. So let's simplify a little. This 2 drops with this 2. The 10 squared over the 2 squared can become a 5 squared for 25. The pi squared is actually surprisingly close to just being 10. So that's going to drop for an 8. This squared is going to be 400 400 over 25 is going to get us a number, that's for sure. I think it's just 8. No, it's 16. And then 16 over 8 gives us 2. And then 2 times 0.35 is 0.75 radians. Is our angular displacement. Could I have just used the calculator for that? Yeah, oh for sure. Should I have? Yeah, oh for sure. I probably made a bunch of mistakes in there. Did I? Anyway, 0.75 radians is going to be able to answer B for us because it's asking how far it would go. So in order to figure out how far it went if it rolled without slipping, we could say that, well, going that many radians is going to sweep out some percentage of the circle. The nice thing about radians is it turns things into linear distances if we just multiply. So if we just multiply this by the radius, that'll give us the linear distance that we travel. And so we can take our 0.75 and multiply by our 0.35, and that'll get us our distance. Sorry, that times 2 is 0.7. I don't particularly care to do that out in my head, and I don't have a calculator on hand. But I will. 0.245 meters. So we've got 0.245 meters as our stopping distance. For C, how would the answer change if the brake pads were located 0.1 meters away from the wheel? So this now, we have to basically go back and reevaluate a bunch of our math. Our wheel wouldn't have changed. So our moment of inertia, our capital R, would be the same. Our lowercase r, which was previously the same as our capital R, would have been different. So our angular acceleration, instead of being 80 over 2 times 0.35, our angular acceleration would have been such that we've got lowercase r times our force of friction divided by our mass times our radius squared. So it would have been 0.1 times 80 divided by 2 times 0.35 squared. So a slightly different number. And that's the number that we would have plugged in up here instead of our old number. I still don't have a calculator on me. I really don't want to do this in my head, so I'm not gonna suffice it to say you actually wind up getting a much greater stopping distance because you have much less torque because your force is being applied closer in. So rim brakes are great in a lot of ways because they get you a greater torque, even though disc brakes, which tend to apply something closer into the center, tend to be higher valued for reasons that I don't understand, but definitely are correct. Let's do the harder problem. It's probably conceptually harder, but involves less just numbers, so I'm much more on board with it. So what would the acceleration of a pulley hanging mass system be if our pulley is a solid disc with a rope hanging off of it, where the disc has a mass of m and it's a disc? For a reminder, the moment of inertia for a disc is 1/2 mr squared. I think just figured that thing out. Yes. And we have a situation like this. And we're asked to find our acceleration for our block. This is why we normally use massless pulleys, by the way. This thing's going to be awful. So, doing this out, here's our pivot, and here's our radius r. Our block needs to accelerate linearly. So the block's second law equations are going to look like the net force on our block will equal the mass of our block times the acceleration of our block. So we need to figure out what the net force on our block is if we want an answer. Well, doing a free body diagram for our block, we've got a force of tension going up. We've got a force of gravity going down. So coming here, I'm going to call anything that causes the block to go downward to be positive, so that I do not have to worry about quite as much stuff being negative when we get to the this friend, the pulley. So mg minus our force of tension will equal our mass of our block times our linear acceleration for our block. For our pulley, our net torque equation is more relevant because our pulley is spinning instead of accelerating linearly. Well, this gets us in a bit of a pickle because our torque will be from the radius times our force of tension pulling down on our object at a 90-degree angle, so I don't have to worry about the angle, thankfully, times 1/2 mr squared times our angular acceleration. And we're in a bit of a pickle here because we've got 3 variables and only 2 equations. We've got our force of tension as a variable, we don't know it. We've got our radius of our pulley as a variable, we don't know it, which is actually going to be a 4th variable. We've got our angular acceleration and we've got our linear acceleration. So we need a way to make this a bit less complicated. Thankfully, there is a way. The length of string that pulls down here is going to be the same as the amount that our pulley rotates if, and thankfully it is, our pulley is rolling without slipping. This is going to come up a lot more later when we do, I think I have to do a whole separate video on rolling without slipping. In order to do that, what this will look like is that our angular acceleration for our pulley will need to multiplied by the radius of the pulley will need to equal the linear acceleration of the rope. And what this is coming from is that the distance of rope that gets meted out, so the linear distance for the rope, will need to equal the angle that the pulley spins times the radius of the pulley. The bigger the pulley is, the bigger the pulley is, the greater a distance a 90-degree spin in the pulley will be. So the more rope will have to travel in order to rotate the pulley. So what I can do from there is divide each side by the radius of my pulley and say that my acceleration will equal my linear acceleration divided by the radius of the pulley. And this is nice because that brings us from having 3 variables, 2 equations, to having 2 variables, 2 equations very quickly, because we've got r ft equals 1/2 m r squared times acceleration divided by radius. This also means that that radius cancels, and if I divide each side by the radius drops. So it turns out, yes, we don't know what the radius of the pulley is, but no, we don't need it because it doesn't matter. Having a bigger pulley will make it so it's harder to rotate, but it will also make it so that you've got more torque, and it'll make it so that you'll get a smaller rotation for any linear acceleration that happens, and those things happen to perfectly cancel out. Great. So now what we're left with is that a force of tension is equal to 1/2 m times our acceleration. So if we come back over here and plug that in over here in our block equation, what we'll get is that mass times gravity minus 1/2 mass times our acceleration equal mass times our acceleration. Mass, thankfully, as usual, drops. From here, if we add the 1/2 acceleration to both sides, what we'll get is that g is equal to 3/2 our acceleration. So if we multiply each side by 2/3, we'll get that the acceleration of the system will be 2/3 as big as it would have been if the pulley had no mass, when the pulley is the same mass as the block that is attached to the pulley. Taking a sec to take stock of that one. So there was 2 really big things that we did here. The first of which was that we said that our torque was going to be equal to our moment of inertia times our angular acceleration. Break up your torque, represent your torque as r cross f. Really, really big step there. So turn your torque into r cross f. In this case, the angle was easy, so we didn't have to worry about it being a cross product versus just multiplying. But if there's a weird angle, make sure you include your sine theta. Next really big step, or really big thing that we did, was we took our angular variables and we related them to our linear variables. All your old stuff for linear acceleration still works. You just have to be careful about when it applies and when it doesn't. All your old stuff for new stuff for angular acceleration can also work. Again, you have to be careful about when it applies and when it doesn't. And to be a little bit careful about the signs if there was more than one torque, for example. So if this was in the middle of a system instead of the end of a system, a lot of times you'll get something like, well, not a lot of times, but you could absolutely get something like this, where there was a block on the other side as well. You'd have to be careful about which of those forces were positive and which of those forces were negative. For me, I tend to be like, okay, well, whatever direction it's going to wind up going, I call that one positive. I don't want to have to worry about my final answer being negative. And that tends to help a little bit. And then you sit and think about like, okay, well, this rope is making this thing rotate in the direction that it's going, so I'm just going to call that direction positive for the torque, and it should work out, and it will. All right, that's pretty much it. Goodbye, YouTube. Hope you have a great night, or whatever time period it is.